Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present epoxies in composites and structural applications. Composites are a blend of two or more components in which one component is for reinforcing, often fibers, and the other component is generally made up of a resinous binder or matrix that is polymeric in nature. These components both retain their individual identities and directly influence the composite's final properties. The resulting composite is composed of layers or laminates of fibers and matrix stacked to achieve the desired properties in one or more directions. Composites are generally orthotropic materials having different properties in two different directions. The reinforcing fiber can be either continuous or discontinuous in length, with strength and stiffness of much greater than the matrix. The resin matrix can be either thermosetting or thermoplastic. Polyester and epoxy composites are the most common matrices in thermoset composites. Resin-based composites are often divided into conventional and advanced composites. Conventional composites usually contain glass or mineral fiber reinforcement and sometimes carbon fiber and are usually produced in stock shapes such as sheet or rod. Advanced composites refer to materials which have properties considerably superior to those of conventional composites and are used for the most demanding applications such as aircraft. The construction and orientation of fibers in these materials are engineered from high-performance resins and fibers to meet specific design requirements. Methods of processing composite materials include filament binding, layout, cut fiber spraying, resin transfer molding, and pultrusion. Composite material technology exploits the high specific moduli and strength of reinforcing fibers to produce low-density, high-performance structures. For many applications of epoxy resins, this involves stacking pre-impregnated fiber sheets, generally known as prepreg, to form laminates. The most important fibers are those based on e-glass, carbon, and aramid fibers, and are available in various forms and with a wide range of properties. Glass fiber composites are the most common type. However, graphite, aramid, and other reinforcements might be used for special applications, for example, aerospace and in premium sporting equipment such as fishing rods, tennis rackets, and golf clubs. Short or discontinuous fibers are not generally employed in epoxy resins because of their poorer reinforcing efficiency compared with their continuous compartments. Mechanical properties of reinforcing fiber is the backbone of the fiber composite technology. Compared to the matrix, the fibers have significantly enhanced strength and stiffness with lower densities. Typical mechanical properties of common reinforcing fibers have been presented here. Graphite or aramid reinforcements are dominating where lightweight is crucial, for example in aerospace and sport good applications. However, where economic considerations are more important, glass fibers are the reinforcement choice. Aramid fibers such as Kevlar, Nomex, and Teflon are the main polymeric fibers. It is also worth mentioning that the filament strength is larger than that of the bulk material. However, the strength of the filament is still determined by the presence of defect, and therefore the reported values are gauge length dependent, meaning that individual filaments with the bundle will have a different strength. This also highlights the need for the protection of the fibers by a resin coating or so-called size during the handling, immediately after the manufacturing. For this application, emulsified epoxy resins are commonly employed for carbon and glass fiber. It has been mentioned that in epoxy composite, often three types of fibers are incorporated: carbon fibers, aramid fibers, and glass fibers. Here, carbon fibers are introduced. Carbon fibers can be manufactured from polyacrylonitrile precursors in a five-stage process: precursor spinning, oxidation, carbonization, graphitization, and surface treatment. To protect these fibers from damage during handling and subsequent fabrication, the fibers are dressed with an epoxy emulsion size resin, which is usually applied immediately after the surface treatment. High-strength carbon fibers are also manufactured commercially from petroleum pitch. This process involves the polymerization of the condensed aromatic molecules at temperatures above 350 centigrade for extrusion melt spinning into fibers, for thermosetting in air, and carbonization at temperatures around 2000 centigrade. The main difference between these two carbon fibers lies in their microstructures. The pitch fibers tend to have radiating crystal structures, while yield a lower transverse strength than for pan-based fibers. Aramid fibers are based on poly-1,4-phenylene terphthalate, Kevlar or Tivaron, and poly-1,3-phenylene isophthalamide or Nomex. Aramid fibers are often produced by an analogous technology to pitch-based carbon fibers. Their highly aromatic molecular structure promotes their stability. However, ultraviolet or UV light can induce the oxidative degradation. Therefore, it is essential to employ protective films in applications where UV environments are encountered. The polar nature of the molecule indicates that the moisture can be absorbed and there is a need to dry the fibers and prevent moisture ingress during use. These fibers have a poor fiber transfer strength and the tendency to fibrillate. Consequently, the fibers have poor compressive strength. Also, the adhesion between the fiber and the matrix and between fiber crystalline planar is poor in these composites. The fiber resin adhesion can be improved by using plasma-type surface treatments. Also, it is possible to increase fiber integrity by gamma irradiation cross-linking, but commercially treated fibers are not generally available. Glass fiber composite is the most common composite type. A number of glass composites are commonly used for the production of glass fibers. The most important is E-glass, but other types are also available for certain situations. For example, S-glass for when a higher modulus is required, ECR glass for acid resistance, and AR glass for alkaline resistance, for example, in cement matrices. The fibers are often prepared by drawing from a bushing below a molten glass reservoir. The most important and commercially sensitive stage in the process is the surface treatment or sizing, which is applied by rubber roller prior to assembly into roughings. The roughings can be either used directly, rewound onto a robin for further textile processing, or chopped into short fibers for the production of chopped strand mats. The surface finish is a critical stage in the process, ensuring compatibility with the resin or matrix and high-speed conversion into composite materials. The finish consists of an adhesion promoter called a coupling agent, a protective polymeric coating or size binder, and other additives, for example, fatty acid, ester, or amide. It is applied in an aqueous medium, and for epoxy resin matrices, this will invariably be an emulsified epoxy resins. Some manufacturers use polyester epoxy resin film formers for compatibility with a range of polyester and epoxy resins. Fibrous mat or reinforcing tissue will have an additional polymeric binder, which can be selected to control the wet out of the fibers in the chosen fabrication process. The adhesion promoter, which is generally a sealant coupling agent, is expected to generate a strong interfacial bond between the fiber and the matrix. The form of the employed fiber reinforcement is determined by the fabrication process. Discontinuous fibers allow complex molding to be manufactured rapidly. The fiber length is generally less than 5 mm in molding processes. It should be noted that there is a critical fiber length exists below which the reinforcing efficiency is seriously reduced. Generally, the critical length of fibers in thermosetting is larger than that of thermoplastics. Fibers of similar length are incorporated into pre-impregnated sheet known as sheet molding compounds or SMC. In SMC, the fibers can be present in various geometries. SMC employs thickened resins but with a wide range of epoxy resins. Often Prepreg technology is employed. For epoxy resins, the predominant fabrication process incorporates continuous carbon aramid or glass fibers, and the technique involves rolling directly as woven cloth or as preforms. The woven cloth can take on several forms: a unidirectional, plain, stain, triaxial, hybrid fiber fabric, or woven tape. The fabrication of fiber composites with epoxy resins is dominated by those involving continuous fibers, lamination in an autoclave, pultrusion, filament winding, and the hot compression molding. In this slide, the fabrication process of epoxy composites will be explained. There are different processes that exist to fabricate epoxy composites, including a spray layup, autoclave, filament winding, pultrusion, compression molding, resin transfer molding, reinforced reaction injection molding, and structural RIM. Spray up, also known as the chop method, works by spraying short strands of fibers out of the pneumatic gun. As the name implies, it is suitable for chopped fibers and used mostly with fiberglass for pipe lining. The autoclave method can be applied to continuous glass, aramid, or carbon fibers, and in this process, stacked prepreg are used in vacuum bags. It is used in the aerospace industry. Filament winding can be used by the incorporation of continuous rowing of glass or carbon fiber. And in this process, resin is carried by the fibers onto the mandrel. This method is used to manufacture pipes and containers. Pultrusion is another method to manufacture epoxy composites, and in this method, continuous fibers of glass and carbon are employed. In this method, wetted fibers are extruded along with the epoxy and cured. It is used for rod and I-beams. The rest of the methods have also been presented in this table. High-performance carbon fiber and glass fiber laminates are fabricated by prepreg molding using autoclave or pressclave, a small autoclave with flat platen press techniques. A prepreg consists of fibers or woven cloths pre-impregnated with the epoxy resins modified with a thermoplastic or elastomeric toughening agent and containing a latent hardener. The latent hardener, such as insoluble dice, is micron size in the resin solution prior to wet impregnation of fibers. The curing can be adjusted by incorporation of promoter or an accelerator. The resin viscosity is adjusted for the appropriate tack by adding thermoplastic polymers or advancing the resin with partial reaction with the hardener. The prepreg is stored between plastic release film in a sealed container in a freezer to avoid moisture absorption. After thawing and temperature equilibration, the unidirectional sheet is cut to appropriate dimensions and stacked at predetermined angles to produce a desired laminate. The bleeding of excess resin facilitates the removal of entrapped air and residual volatile impurities during the consolidation of the prepreg into a void-free laminate. Due to the exotherm nature of the chemical reactions and the risk of temperature buildup in thick sections, the curing schedule should be carefully controlled. Prepreg molding techniques have a complicated technology, but offer the mechanical engineer the opportunity to orient fibers in the direction of the principal stresses within complex structures. The main types of thermoset in composites are epoxy and unsaturated resin such as polyester or vinyl ester. The epoxies are generally of relatively low molecular weight and satisfy the requirements of an appropriate matrix for composites, which are low viscosity for fiber impregnation, high reactivity and curing, no volatile formation, and yielding good mechanical properties of the cured resins. Other thermosets, for example phenolics or polyamides, produces volatile organic compounds since these involve condensation rather than step growth or addition polymerization. Therefore, in those systems, because of volatile formation, high pressures and more complicated cure schedules are required to prevent damage accumulation. Epoxies are generally satisfy the above criteria, whereas it offers a low shrinkage. The glycidyl ether of bisphenol A with 2 to 4 oxyron rings form the basis of the general-purpose resins for both adhesives and composites. The glycidyl amines have a higher functionality and potentially high cross-link densities and glass transition temperature and form the basis of the resins for aerospace composites. Typical resins for laminates or composites are presented here. The choice of the resin and hardener determines the cure procedure and the viscosity profile during cure. Other modifiers, for example, polyether sulfone and phenoxy resins are also used to control process variables. Moisture absorption leads to a significant reduction in glass transition temperature of the cured resins, which seriously limits the maximum service temperature. To mitigate this effect, highly cross-linked resins with the incorporation of the toughening modifiers are required. The thermoplastic modifiers can also be used. However, in contrast to adhesives, carbonyl terminated rubber or CTP and toughened epoxies are not generally employed for composites. Other important systems employ thermosetting modifier such as bismaleimide or cyanurate resins to achieve a high temperature performance with durability. Hardeners and catalysts also have a substantial influence on the cured resin properties. Amine hardeners react with epoxies to form hydroxylamines. The presence of the hydroxyl groups promotes the adhesion to the fibers. However, the polarity promotes moisture sensitivity. Therefore, hardeners or catalytic systems which provide a less polar molecular structure are preferred. For industrial lamination, tertiary amine-promoted anhydride cure is often employed. Nodic methylene tetrahydrophthalic anhydride or NMA is commonly employed with diglycidyl ether and tetrafunctional glycidylamine with benzyl dimethyl aniline BDMA. Microsize Dicey also provides latent curing ability to prepreg with improved shelf life. Both high and low temperature curing systems are also available. Without the presence of an amine accelerator, the rate of curing is determined by the melting point of Dicey, which is 165, at which temperature it dissolves into the epoxy resins. With the aid of the accelerator, the curing temperature can be reduced to 120 centigrade, which is advantageous as it helps to control the exotherm during the cure. However, low temperature curing based on Dicey increasing the probability of the presence of residual dicey hardeners in the resins. Curing of epoxy resin with dicey have been presented here. Dicey is used in catalytic quantities of 4 to 6 pHr. It should be pointed out that the complete reaction of the epoxy group is not normally achieved except after long times at the high temperatures. This highlights the need for an appropriate post-curing to reach higher heat distortion temperature and chemical resistance. In fact, the mechanical properties of epoxy resins are dependent on the hardener, curing system, and time temperature profile. The effect of post-curing on mechanical properties is attributed to the increasing cross-linking after the post-cure, consequently result in an increase in the heat distortion temperature and Young's modulus. However, there are exceptions to this where a higher glass transition can rise along with a lower modulus since the gaseous state is frozen in at higher molecular free volume. The joining of composite materials involves some special problems not faced with other materials. Thermoset composites are joined by adhesive bonding and mechanical fasteners or with a combination of mechanical fasteners and adhesives. Mechanical fastener must be sized to avoid fiber crushing and delamination. Adhesive may also be used to bond composites. Adhesives must balance strain and flexibility. A significant advantage of using adhesives for composite join is that adhesive bonding does not require the composite to be drilled or machined, processes which drastically weaken the composites. A cut edge also allows moisture wickup and further weaken the structure. The three adhesives most often used to bond composites are epoxies, acrylic, and urethanes. Due to the similarities in chemical and physical properties, epoxies are especially reliable when used with epoxy-based composites. To bond large composite structures, room temperature curing adhesives are preferred. Employing room temperature epoxy adhesives, expensive fixture tools, and curing equipment required for higher temperature cure adhesives are eliminated. However, room temperature epoxy adhesives are not suitable for large, high-speed production runs as their curing time is long. Moreover, there are other considerations that also exist when using epoxy hardeners for composites. Some composite materials are sensitive to the heat required to cure many epoxies. Moreover, epoxies are too stiff and brittle for flexible composites. Composite structural adhesives are often supplied in two basic forms: semi-solid, beta-stage film, and thixotropic paste. The film adhesives are cast or extruded onto carrier fabrics or films and partially cured to a semi-solid. They can easily be handled, cut, and applied to the joining area. There is no need for mixing, metering, or dispensing of liquid component. These adhesive systems are activated by heat and pressure. The semi-solid beta-stage film liquefies by briefly on application of heat and then cures to an insoluble state. Epoxy polyimides, epoxy nylons, epoxy phenolic, and nitrile phenolic adhesives are available as beta-stage film. Paste adhesives are supported as either one or two component adhesive systems. They can be used in application where pressure cannot be applied. Some two-part pastes cure at room temperature and some others not. Epoxy urethane and acrylic adhesives are available as paste adhesives. Recommended surface preparation of many composites simply consists of a solvent wipe to remove dirt followed by a mechanical abrasion. The abrasion degree is important and it is desired to be set to a level where the glaze of the resin surface is removed but the reinforcing fibers are not exposed. Many surface abrasion methods can be applied to composite parts, including light sanding, grit honing, vapor honing, and other methods. In some cases, a primer may be used to coat the composite before the adhesive is applied. Another technique, a peel or tear ply, is used on the composite sheet as the outer layer of the composite during its production layup. This outer ply is then peeled away just before bonding, which fractures the resin's matrix coating and exposes a clean, fresh, and a roughened surface for the adhesive. This method is fast and eliminates the need for solvent cleaning and mechanical abrasion. Thanks for your attention. I hope you found this video interesting. Please share your thoughts, comments, and questions, and I will come back to you soon.